Okay, so I'm going to start. So thanks everyone for being here. Um, so I'm going to present a paper which is called MaskGAN. It's by research done in Google. Um, you might notice that one of the fellows that did that paper is Jan Goodfellow, which is quite famous because he's the inventor of GANs. And so yeah, let's start. So the idea of MaskGAN is to make some text generation, and to learn how to do that is going to fill some blank in some text. So basically, I'm going to spend a bit of time in the intro to explain some basics about text generation, because I think I'm going to talk about myself. From the previous cohort and last cohort, we've mainly have been working on computer vision. And I think most of the papers that were presented were related to computer vision as well, except last week by Sergey. But this is one of the first, I think, about text generation. And because the cohort is a bit new, I think it's good to spend a bit of time talking about general knowledge about text generation, and that's also because it's used later on the paper as a pre-trained states. So that would be the start, and then I will give more detail about how they use a GAN way to do text generation. It's a bit of a challenging paper to understand, so I'll try my best to clarify everything. If you have questions, feel free to ask them. And if someone has read the paper and think he understood something in some other way or some better way, feel free to say something. Okay, so what is text generation and neural text generation? So it's like models that are used to generate text by sampling words sequentially. So basically, you're going to generate a word, and each time you're going to generate a new word, you will be conditioned by what was the previous word. And this was quite recent, known under the name of recurrent neural network. And it had gained a lot of attention because it has reached, push up the state of the art a lot for machine translation and summarization benchmark. And so I think the basic idea in text generation is recurrent network. And so most of you guys know from computer vision, this feed-forward network, where basically you have an input layer and then you got some hidden layers, and you just push the activation to the next layer. The difference in recurrent network is that the output of one layer is feedback in. So there's a connection that is going to feedback the output within the neuron again. That's why we say it's recurrent. So another way to represent a recurrent neural network is this representation. I'm quickly going to talk about it because that's going to be the representation we're going to use a lot after. So here we got some input, and then the output is the generated output from the recurrent network. And this is feed again, so that's why it's recurrent. So it's the same graph as this one, but unrolled, so for better understanding. And you have to understand that this A thing at different state is the same. It's a different cell state, but it's the same cells. That's why it's not like a bunch of different layers. It's the same cell. So it's quite important to be clear about that. So one quick example, for a machine translation, is we have this cell that is going to have this state changing over the time at each time step. So this is time, it's each of these or time step. And each time we got an input at one time step, the cell state is going to change and be in a new state that we keep, and then we put the new input inside. And for machine translation or things related to text generation, we need to at some point we got this cell, and it's going to give us a probability distribution of possible words to output, and we have to sample one, to select one, and this selection is fed back in because we want the network to be aware of what it has been predicting so far. So it's quite different from computer vision. And though there was a lot of excitement about recurrent neural network, and a lot of people have been playing with it. Like I know some guys tried to generate the last 3 pages of Harry Potter with a recurrent neural network, and it was quite fun because they had a text that kind of, it was proper English. It was somehow funny, kind of make no sense at sometimes, but still it was really, you could read it and understand pretty much what he was saying. And people realized there was a big problem with recurrent neural network. There's a standard RNN is like to remember the context. So imagine when you have a short gap in your sentence and you have this is a blank and you want to predict that word. Here, like the sentence is quite short. So let's say like we got clouds as an input in the blue inputs here, and there we want to predict sky. So because it's close to each other, somehow the network remember the context that was just before, and it would make sense for it to predict sky. But if we look at the longer sentence, here we have a longer gap with a sentence which can be like, I grew up in France from 0 to 10 years old, blah, blah, blah. I am fluent in, and then we have to fill up the blank. For us as human beings, we know like France is a big part of the context. So if you remember that, then you can predict French. And there, the further you get, then the RNN is going to have some trouble to remember the context. It's like it has a very short memory. And there, like this input happens too early, and later the recurrent network is not going to be able to predict the proper word because it only knows the states that was just before somehow. That's why LSTM was invented, and LSTM stands for long short-term memory. So I won't detail everything because I'm not even sure I can explain it properly, but the idea is like this is kind of a standard recurrent network, and LSTM is going to use more gates and more multiplications. So we say that LSTM got different gates. There is a forget gate, which is something that is going to be able to forget what is not relevant at some point, but keep what is relevant. We have an input gate. So when we get a new input, we're going to somehow select what is relevant and what is not, and then we're going to combine that. So we noticed by doing those that LSTM were much better at keeping a sense of the context in the text, which is quite important when you want to fill some blanks in text or to generate random text, like to have a network that is able to remember the important context. So LSTM is very well used in text generation. It's quite of a standard. And so I've been talking about that because it's going to be used later on for our generator. But first thing first, so why are we talking about MaskGAN? So here, remember, the goal of this MaskGAN is when you have some text with blank, you want to be able to fill up the blank, and that should make sense. So it's what we call a sequence-to-sequence architecture. So we have a sequence with some blank as an input, and we want to output a sequence with words that has been used to fill up the input, the blank. So we call it MaskGAN because we use what they simply use a mask. So imagine you got this input sequence, which is like a bunch of words from X1 to XT. Then you will have a corresponding mask from M1 to MT, which is just a bunch of zeros and one. And 0 stands for like remove this word and put a blank, and 1 stands for keep that word as it is. So that's how they use a mask for getting some blanks. They don't really clarify much how this select like this mask, like how many zeros, how many ones, but that's how they use it to get this blank input sequence for the network to generate then some fake or generated text that is not the ground truth. So here is
so they did, excuse me, they did make clear that the mask is continuous. It omits a group of continuous words. It's not just random words everywhere. It's a group of contiguous words.
Sorry, once again. Okay. From my
sorry. Yeah. What I was saying is that the mask is contiguous words. That is, words that are adjacent to one another. So it will omit a group of 3 words or something like here, and then a group of 5 words later on, something like that.
Yeah. Okay. Yeah. But I'm just not sure like how they decide like if they get 5 words contiguous one after another to remove only 1 or only 2. But yeah, okay. Thanks for the clarification about that part. And so here is the generator. So basically this is here the input sequence for our generator network, where we've been applying a mask here. So we got 2 blanks, and all this encoder and decoder, this is LSTM actually. This is like what I've been explaining before. So they've been training a language model, a LSTM language model, on the data to get like all the weights for the encoder and the decoder. That's why I've been talking about LSTM before. And the idea of the generator is like to go through this LSTM network with the blank, and then we have a cell state, and the decoder is going to output some letters or words and feed it back to the decoder. So then, sorry, the idea is like here we got this, here we got this generated sequence. So we had a sequence with blank, and then we got a sequence with generated text, generated words. And so like what is different in the way, what they claim that is different that they're doing is like they're gonna give the decoder the information about the mask. So somehow they tell the decoder which X, I, or ground truth or generated. So like in a standard LSTM model, if you have to fill up tokens, then you're just gonna have like this. So like the probability of this output here is gonna depend on what happened before, but you won't have the knowledge of the mask. And that's what they say that is a big difference for them. So they give this mask to the decoder. And I guess my understanding is like, since it's like some kind of extra knowledge for the decoder that can influence its confidence. And for example, if you knew that the 5 previous words were ground truths, then you know the cell state is pretty stable, it's based on the ground truth, so you might be more confident. And if it's not the case, if it was like generated for the last 4 times, then you might be a bit less confident. Okay, so that was the generator part. And we've done all that to get the generator to finally, we've explained the mask, and then we have a generator, and then we can do what we call a GAN. So a GAN stands for Generative Adversarial Network. I guess most of you guys know about that. So to quickly explain what is a GAN, and GAN was invented by one of these guys from the paper, Jan Goodfellow. So we had the generator we've been talking about is able to generate some sentence with some filled up blank. And we are going to have as well a discriminator. And GAN, the idea of GAN is to have a discriminator that can say if an input is real or fake, if it was generated by a network, or if it was proper data. and it add a lot of attention, like for on images, to generate fake images. Maybe you've seen like these fake faces generated by GANs, which is quite impressive because you can't really tell yourself I mean, for a human being, it looks like a real person. So the idea is like they're going to compete in an adversarial way within each other until like, so the discriminator is going to tell us real or fake, and the generator is going to learn from that, and at some point is going to be able to generate a fake image which looks like a true image. And that's what we are doing with MaskGAN. It's like we got some text generated, and we want the discriminator not to be able anymore to distinguish like if it was generated or if it was a ground truth. That's pretty much the idea here. So yeah, that's exactly what I was saying. Here comes the discriminator. So I always done the discriminator in the paper. So the architecture is the same as the generator. We had this encoder and decoder that were pre-trained on the LSTM language model. We're gonna get as an input sequence. So it's like, again, it's a sequence to sequence thing. Input sequence is gonna be the generated sequence. And the difference is gonna, at each time step, we're gonna output a probability. And we also give to the discriminator the real context. So that's why we got the color here. Like the discriminator knows which word are ground truths and which word are generated. They explain why they need the discriminator to be aware of the masks that was used. It's like to make sure it's able to learn and to avoid critical failure mods. So they give some example, like, let's take this sentence, which is director guide the series, which obviously like there is a problem here where when the generated sentence, the blank was director generated twice. And we can see that we have two different valid sequence, like the associate director guide the series or the director expertly guide the series. Both of them are equally valid. And if you have that, then it will assign an equal probability for both of them. Then the network won't be able to detect that this generated bigram director is a fake text. That's why they claim they should give the mask to the discriminator. Guys, I think someone got his microphone on. Can please turn it off. Thanks. So, and okay, so here so what they're saying is like the discriminator is going to compute a probability for each token of being real, knowing the true context. So we see like this is exactly what the discriminator probability is going to output. The probability of this word at time t to be real, knowing what we've been generating before and knowing the mask. And from that, they define a reward, which is the log of that probability. So the goal of then they do some kind of reinforcement learning, and the goal is like to get the bigger reward you can. So the idea is like to push up this probability to maximize the prob of X generated to be real X. From there, with this reward, they apply some kind of reinforcement learning. So that's where I got a bit lost. Like, so they explain that because in text generation, at some point you have your language model is going to output some probability for all the possible words in the vocabulary. Then you have to choose one. And when you do that, then you do some sampling and it becomes a discrete problem. So it's not fully differentiable anymore. And they claim, and I'm quoting them because it's kind of unclear for me, I'm sorry about that, using one of the reinforcement family of algorithm, we can find an unbiased estimator of gradient. And they came up with this formula. I don't really understand the formula, to be honest, but the idea is like, since they got the gradient, then they can apply some, after they can apply some standard GAN learning. And then they apply this GAN learning to get the generator and the discriminator to compete with each other, and pushing the generator to generate more full of sense text generated word for the blank. So okay, so for the evaluation, as they say in the paper, it's actually very difficult to evaluate GAN models, because what is making like a fake text fake or true text true? I mean, like, some text could be generated by AI and be full of sense and but weird, or like full of sense, and it could be the same from a human being, or it could be grammatically correct but weird, and nobody's going to say that. So it's very difficult, like, to get automate way to evaluate GANs, and the best way is usually like human evaluation. And that's where, like, for example, when you see fake faces generated, as a human being, you cannot tell if this is a fake or true faces. Then, you know, as a human discriminator, you're getting fooled by the generator, so it means it's working very good. So in the papers, it like talk about perplexity. They give some sample generated by this MaskGAN compared to a language model. That seems better with the MaskGAN, but it's like not a proper way to, I mean, to me at least, like, to, it's not by giving few examples that you said this model is better. And I think the best evaluation they got is the one they have done with human using Amazon Mechanical Turk, where basically they got some two sample from, so they used EMDB reviews and they put some blanks, and then they generated one sample with MaskGAN and another one with a standard language model, LSTM. And then they asked some human being to read both of the reviews that were fake, and ask them three, like, which one was the best from a grammatical point of view, from a topic point of view, so like more the context, and overall. And what we see on the two first line, which is quite interesting, it seems like a human being really think that the MaskGAN generated text was making much more sense to them. But what is interesting as well is that they did the same experiment with real sample and MaskGAN sample, and we see that actually, like, people are not, like, human beings are not getting fooled at all, and they're basically, or it's quite easy for them to see when it's real and when it's not. So it seems like they generate more senseful text, but still not good enough to fool a human discriminator. What they claim in this paper, and I think it's quite interesting for text generation, is that they have a loss function that won't be penalized if it's not using the maximum likelihood estimation. So a lot of text generation loss function, basically, like, if you want to reduce the loss, you have to pick up the word that is the most with the highest probability, but somehow you only, like, learn by heart some text that was learned by training, and you try to produce exactly the same, like to follow the probability distribution. And the way they compute the loss function, somehow it's in a way that it won't be penalized if it's not the maximum likelihood, if it still makes sense for the discriminator that is a language model. So I guess this is quite interesting to say that indeed, when you generate text, you don't want to generate like what is the highest probability or the closest to the training. You kind of want this random thing to happen, or to generate something new that makes sense. And I think they somehow tackle that, which is quite interesting. So at the conclusion, I would say, like, this paper is full of good ideas. It's a challenging paper. It's not so easy to understand. I haven't got everything myself. I hope I somehow clarified a bit for you guys. I think like what is interesting in this paper is this way like they kind of like mix together a lot of different knowledge to go somewhere, and that's quite impressive. But on the other hand, it seems like almost nobody used MaskGAN. Like I mean, there's only one. I've found only one implementation for TensorFlow, but TensorFlow is Google, and this guy worked for Google, so they did one implementation. But I haven't found any blogs or anyone talking really about MaskGAN. So it seems like somehow because Jan Goodfellow was the inventor of GAN, this paper got some attention at the beginning, but nobody really seems to use it for real. So yeah, that's somehow a bit, something to think about. Like why nobody seems to use that paper? Is it too difficult to understand? Is it not really useful or whatsoever? Yeah, that's it from my side. Do you guys have any question?
Yeah, thanks, Baptiste. That was really a good presentation. So I have a question. He refers in his section 5. I actually read the whole paper except for the section with the equations in it.
Okay.
So far.
Yeah.
Anyway, the section 5 where he compares results, he talks about MaskLM, MaskML. Sorry.
Yeah.
And I didn't get what MaskML was. That's not something that he developed in his paper.
I think the paper is very difficult to understand. I think I understood what was that MaskMLE. So MaskMLE is based like refer to maximum likelihood estimation, and I think that's they applied the same mask, but instead of using a GAN loss, they use this maximum likelihood loss. So it's like a language model, but they give that language model the knowledge of the masks that was applied. Yeah. So it's like better than standard language model because it knows the masks that was applied, but it's still not a GAN training, it's the standard training. So I think that's what they refer to, but I do agree it was not clear.
Yeah, I think that's good. I didn't notice that the first sentence there, that makes it clear, I think. So, but then he said, to your point that MaskGAN doesn't seem to be used, he did mention that it falls short of state-of-the-art performance for these tasks, and he did say that maximum likelihood based methods do better. So that they are the state-of-the-art. So I guess that's why nobody uses.
That's why nobody. I guess maybe nobody mentioned it in the paper because nobody managed to beat them because there is a state of the art. But I mean, there is no. I haven't seen like blogs on Medium or whatever, like people playing with GAN to generate text. They always use LSTM or things like that. But maybe because it's a bit more difficult to use, I don't know.
Yeah, and I like the idea of the blanks, of having groups of blank words. Again, I agree with you. He wasn't very clear on that. I mean, how do they generate the masks? I mean, are there 3 words missing or are there 5 words missing? And where does it happen? Does it happen randomly throughout the whole text? Or so I don't understand. But he did mention somewhere that in the models that he used, he actually omitted 50% of the text, I think. Somewhere in there he said that, yeah, the masking rate is 0.5.
Yeah. And
so, yeah, right there. So that's pretty amazing.
Yeah.
And then I know that I'm not really familiar too much with the field here of neural translation and so on, and neural text generation, but there are methods based on bidirectional LSTMs that so they don't just remember the context before the word, but that they're trying to guess, but also they know something about the context after the word.
Yeah.
And maybe that's why they are doing better than maybe that's why they're doing better than this method or something. I actually wasn't clear what is the state of the art, which methods he's referring to, which particular papers he's referring to that get state of the art performance on these data sets.
Yeah, I do agree with you. It's not that clear, but I like the idea of like having a mask that like somehow you got some knowledge of what happened after and before instead of only having the knowledge of what happened before. So that's, I guess,
Yeah.
somehow how they managed to get something better. And I think it's
Yeah.
quite to use this blank. So you got knowledge, you leverage more knowledge instead of just what you've been generated so far.
Yeah, and it's really similar to a problem that I've noticed, that I've come across before in time series analysis, where you have time series, let's say a signal, and you have missing regions. So, like, say your sensor wasn't collecting data during certain times, it wasn't giving you data, and you want to be able to fill that in. And that's a really difficult problem, because if you try to predict something based on what went before, you might do well the first few data points, but then it starts to get noisier and noisier and noisier. The farther in, say you have a blank region with, many missing data points. The farther you get into that blank region, the worse your prediction gets. So it's a similar problem that to replacing words in a blank sequence, and it's just really difficult because the noise. If you've ever seen a plot of the noise gets worse and worse and worse the farther you get into the unknown sequence. And so I can really appreciate that problem that you spot here.
Yeah, and I think that's the idea of the mask. It's like somehow it avoids you to go too far away, when you come back to ground truth, and that's avoid yourself building like a model that is just getting more noise and going crazy. So yeah.
Yeah, and so I wonder what state of the art is in language predicting what comes next. I mean, do you have a sense of whether they can do well on, let's say, 3 or 4 words, or 10 or 20 words, or 100 words? I'm sure that it's somewhere in between. I mean, I'm sure they can do well on 3 or 4 words, but then it gets harder and harder if you go up to like 10 words or 20 words, and maybe that's where the state of the art lies right now. And then it's impossible when you get to like 100 words.
I don't have much information about that, but I should check that for sure. It's an interesting point, yeah.
Anyway, thank you so much for the presentation. It was really
Thank you very much. Anyone else got a question? Okay, good. So I think we are done. I will share the slide on the Slack. Thanks everyone for attending, and have a nice day. Bye-bye.